In this video, we'll continue our discussion of the chain rule by figuring out what implicit differentiation looks like for the chain rule. All right, so we're going to make some assumptions here. It's going to be, this method's kind of neat. So take a look at this. We have a function, we'll call it w, okay? And w is a function of x and y, and we're going to say that that function is uniformly zero. Now, this may feel weird, like, oh, we're not going to run across very many of those. Well, I'll show you how to manipulate your function to create a new function that is uniformly zero. All right, where f is a function such that y is a function of x, that's what that means, and x is the only independent variable. Okay, so we have a function where, okay, and then a couple things here. Notice that we're interchanging w and f. Those are the same things. Okay, so this is our chain rule here. If I want to find the partial of w with respect to x, the formula says to split it with these intermediate variables, we're just going to use one of my actual variables as the intermediate variable. So that's just using the chain rule. We can break that up, right? However we want. I know it seems silly to do that, but you'll see where we're going. Okay, the function being uniformly zero, and this is w, by the way. If w always equals zero, then w with respect to x, the derivative of zero with respect to x is still zero. So I know this equation. I'm going to rewrite it here. I know the whole thing's going to be equal to zero. Another thing I want to point out, this dx is just a 1. So rewriting everything here. All right. And then I want to point out this partial here can be a regular derivative. The reason being is because y only has one variable, which is x. So I don't need to say partial when it's only x. Okay, you see probably where we're going here. I can solve for dy dx by subtracting partial of f with respect to x and then dividing by partial of f with respect to y. Your curriculum, textbook, typically in notes, you see more like this. Minus, and then blue f partial over y partial. Just easier, I think, on the eyes to see what we're doing there. So this is our implicit differentiation that I can find dy dx if I just take the partial of f and the partial with respect to x and divide it by the partial y and make that negative. Okay, so let's give this a try. Now, like I said, I was going to point out what this means. So let's take a look at this. We have this whole equation here, and regardless of what the equation looks like for this equation, I can move everything to one side and always get an equation that's equal to zero, right? I can add all the terms to one side. That's what we're talking about. I want the equation to be uniformly equal to zero. Well, the function now in question for this would be f of xy is that 2x squared plus 3 times xy to the 1/2 minus 2y minus 4. That is my function. It seems silly, but they didn't give us a function. They just gave me an equation, and that's the whole point, right? The whole point is implicit differentiation is that I can't solve for y, but they're asking me for dy dx. But now I have this new function f, and I know that I can find dy dx if my function always equals 0. Well, that's what this says. It's always equal to 0. And all I gotta do is the negative of the partial with respect to x over the partial with respect to y. So we just have to find each one. All right, so the derivative with respect to x, we have 4x. The derivative there, I would think about it this way. I think it's much easier if I just split that half. I can do that with powers as long as it's being multiplied inside, not adding or subtracting. So the half would come down, giving me plus 3/2, x to the minus 1/2, y to the 1/2. And then the last two terms are constants, so they're not there. The derivative of of f with respect to y, the first term is a constant. Okay, the next term is going to be almost identical, except for the y is going to be the negative 1/2. You can think through that if you'd like. and then the y partial derivative with respect to y of minus 2y is minus 2. So we have our derivative now. dy dx is equal to, right, minus 4x. I'm just going to distribute the minus through. I'm not even going to clean any of this up. That's totally fine. Over 3 halves, x to the 1 half, y to the negative 1 half, minus 2. We could clean the halves up if we really wanted to. The back of your book would probably do that. I think that is a great answer, and going any further feels like I'm doing work that I could have just solved for y if it was possible, which, looking at that equation at the top, I don't think we could have solved that for y nicely. Right? That's what we mean by implicit, is that you're given an equation that's very difficult to solve for your dependent variable. And this method, using that formula, will allow us to get there.